Hello everyone, for this video we're going to learn the Prelab 2 for sp015. Ready? So for this experiment, free fall and projectile motion, our objective is to determine the acceleration due to the gravity for the G. We want to get the G experiment, and we want to compare it with G theory. G theory, gravitational acceleration for the theoretical value is 9.81 meter per second. Okay, this one. Now in this experiment, we will be doing two experiments. The first one is a free fall motion, and then the second one is the projectile motion. So let's take a look at the free fall motion. Our equation that we'll be going to use is h equals to half gt squared, and we're going to compare it with the linear graph equation, which is y equals to mx. We don't have any plus c over here because based on this equation we do not have any value for the y-intercept. When we compare these two, we can see that the y-axis will be the height, and then the x-axis will be the t squared. We're going to get that, and then from there we can see that our gradient is half g. So the graph should be like this. You're going to compare, sorry, we're going to do it like this. The y-axis is the height in centimeters, if I'm not mistaken, and then the what do you call that, the x-axis is the t squared, and we're going to get this in seconds squared. From this we can get our linear graph. It must pass through the, theoretically we will pass through the origin, but even if you don't get pass through the origin, it's okay. We're going to do the discussion on why is it error for that in the discussion in your lab report. Okay, and then from this we can get our triangle for the gradient. So your gradient should be m, which is the gradient symbol for the gradient, equals to half g. So from here onwards you will get your g equals to 2 times your gradient value. Okay, this is the setting for the free fall experiment. You're gonna have your steel ball over here, and you will be having an electromagnetic ball release, and then when you press this button, this ball will pass through a sensor. The sensor is at the trap door over here, and it will connect to the starting point over here, and once you release it, it will start to trigger the timer to start, and then once it reaches the trap door, it will stop. So this is your h, the height of the steel ball to the trap door. Okay, next we have the second experiment, which is the projectile motion. So the equation that we'll be using is this one, h equals to 7 over 10 r squared over gt squared. Then we're going to compare it with linear graph equation. So for this one, y equals to mx, so we can get our value on the y-axis as the height, and then the x-axis is the r. So this is the x-axis value. So if you try to sketch the graph, it's going to be like this, h in centimeters, and then we have another one which is the r squared. This one is also in centimeters, centimeters squared. And then we're gonna get our linear graph, and theoretically it should pass through the origin, but even if you did the experiment and you didn't get passing through the origin, it's still okay. We're gonna do some discussion in our lab report. So from here we can see that the gradient equals to, so the gradient m equals to 7 over 10 gt squared. Here m equals to 10 gt squared. Now m we can get from the calculation of the triangle. It's easy, but the problem, because we want to get the g, so there's a problem. We do not have the t squared. We do not have that value. So where should we get? If you look at the if you look at this one, so This is the setup for the projectile motion. So you have this one, the retort stand, and then the curvy path like this. This is your table, and this is our H. This is your capital H. So once the steel ball projected, okay, height to ground, what we have here, we have the R and we have the capital H, which is the height of the table. So here, if you look at the step number 6 in the procedure, you can say by referring to the graph of H against t squared from experiment A, obtain the value of t squared for the H, which is the height of the table in the second experiment. This is a projectile motion. So we want to get the t squared for this particular height, which is the height of the table. So we're going to go back to our sketching. Okay, you are going to plot the graph for experiment A, and then from there you should get the height of the table in experiment B, and then you're going to extrapolate and get the t squared over here. There. Once you get the value, you're going to put it back into the calculation of your gradient. Let me see, where is it? Or here, you're going to put it back into this t squared equation. Okay, then you can get your G. Okay, so 7/10, the gradient times the t squared, where you can get this from the graph of the H against t squared in the experiment A. Okay, for the free fall, we have to repeat our, first we have to adjust the height above the point of impact, which is the photo gate, no, the trap door, and then switch on, and then we set the timer. You just release the ball, and then you're going to repeat with different height. Okay, you have to repeat with different height, and then you have to have at least 6 different reading, which is 6 different H. Okay, so this is your data table. Sorry, this is your table. This is your number of reading 1, 2 until 6. This is at least, it says in the procedure here, at least 6 reading. You can do 7, you can do 8, but you cannot do 5 or less. Okay, so this is your height, the uncertainty. Do not forget the uncertainty for the whatever measuring instrument that you're going to be using to measure the height, and then the time taken. Again, do not forget the plus minus, the uncertainty for that particular measuring instrument that you use to measure the time. And then you have to have extra one more column. This one is for your t squared, because you want to you want to plot the height versus t squared, right? So this one is for the free fall. For the projectile motion, what you have to have is you're going to record the height and then the range. So your table should be like this one. So you have to have readings. Look at the procedure, whether it says that you have to do 6 or more, and then the height. This is the H, small h. The small h is this one, the height from the steel ball to the curve railing. So this is your h from the surface of the table to whatever the bottom of the steel ball. This is a small h. This is different from the big H here, capital H. Your capital H, because it's only the height of the table is the same throughout the experiment. So we are going to put the height of the table, H-E-I-G-H-T, of the table, sorry, H besar, and then you measure whatever value that is. Don't forget the plus minus, because you get this reading from your measuring instrument, and don't forget the unit, because it's only one reading. So that's why we have to put it at the top of the table instead of the rest. Instead of this one, put it in the table for the repeated readings. So for this one, you change the height. This one you change the height, maybe you put it here, next reading you put it here. So for each reading, you put it in the table. And then the range, this is what we get. You measure the range from the pendulum bob over here. This is the starting point to the where the ball drops. Okay, so this is your R. And then because if you see here, it asks us to plot the H height of the curve railing just now to the R squared. So we have to process this data and add in another column for the R squared.